Another really impressive feature of Kubernetes is its ability to quickly scale up replicas of an existing service. This really goes along the lines of helping ensure high availability of your solutions. You can use the kubectl scale command on the deployment resource in order to set a new replication factor. This command should set the replication count and the spec.replicas value to 3. You can list the resulting number of pods to verify that the action has completed successfully. You should see 3 pods in the resulting output. Another great feature of Kubernetes is auto-recovery. Kubernetes will automatically watch for changes in the count of pod resources, similar to how you might run this command, kubectl get pods -- watch. Any changes to the active list of pods will automatically be echoed back to you on the command line. In another terminal, we can try deleting several pods by ID in order to see what happens when the spec and status move out of alignment with each other. kubectl delete pod followed by the pod IDs will delete multiple IDs by resource by ID, multiple resources by ID. This full example, if you copy and paste it from the slides, should grab the top 2 pods from your list, or 2 random pods from the list, and delete them. You can run kubectl get pods to see what happened and how many pods remain. The expected result after deleting 2 pods is Kubernetes should automatically notice that the replica spec and the replica and the replica value in the status field are out of alignment. The spec will suddenly say 3 while the status says 1. At that point, Kubernetes will provision 2 new pods on the API in order to fulfill our requested replica spec of 3. Once this is back in alignment, Kubernetes will continue to actively check to make sure any pods that need to be added, restarted, or removed are taken care of and managed effectively. Some other things to note from this section: you can use the dry run flag to generate new resource specifications without performing API operations directly. And Kubernetes uses a declarative style specification for comparing the spec and the status, allowing you to kind of set it and forget it, which hopefully makes a lot of your coding more simple because you can, to some extent, rely on services to be highly available. Replica sets are the last topic we'll cover in this Kubernetes fundamentals section. A replica set provides replication and lifecycle management for a specific image release. I have a few command line examples shown in this slide here that show how you might use kubectl set image on a deployment resource in order to change the image tag from :latest to :v1. This should perform a 0 downtime rolling update of the deployment resource as long as there are a minimum of 3 available. You can use kubectl get rs to view the rollout as it spins up replicas on an initial replication controller and spins down replicas on the older replication controller. To view the list of previous rollouts, you can use the kubectl rollout history command on the deployment resource that you would like to investigate. And you can roll back by running kubectl rollout undo deployment and deployment ID. Having this standardized software delivery, containerized software delivery completely standardized and included as part of the platform is really, really great to have, you know, this solved at a community level. And it's great to have higher level, have this fundamental solution solved in a really elegant way so we can build higher order abstractions by recycling these fundamental primitives on the Kubernetes API. These are all meant to be very low level building blocks that allow higher order distributed solutions to be built on top. And that's really what we're doing with OpenShift. Replica set attributes. Replica sets provide lifecycle management for pod resources. This sounds very similar to what I just described with deployments. The main difference is deployments create replica sets to manage pod replication per rollout or per change in image tag, per change in pod spec, per change in environment variables. Each of these changes on the deployment resource will in turn generate a new replica set, which will generate new pod resources in turn. If we try to delete pod resources first, the replica set will automatically create new pods in order to fulfill its internal specification. And if we delete replica set resources that are active, the deployment resource will automatically recreate any replica sets that go missing, which will in turn recreate the pods. So you really have to kind of delete these things from the top down, starting at the higher order abstractions, which should in turn clean up their lower level abstractions as part of their teardown process.